I don't know why I did that. I'm autistic. So, so today we're going to do tangent spaces. Sorry, Phematica, but you're slow and fat, and algebraic topology is actually pretty fun, but I don't care. And you're only like at like what? You haven't even gotten to homology, so take your time, because I'm okay. So we're gonna do tangent spaces of manifolds, which is going to get into how we can differentiate, do differentials on manifolds, like do calculus on manifolds, basically. Tangent spaces are very much the, is it, would I say bread and butter? I don't know, some foundation that builds on, it's the foundation of manifold theory. I mean, not manifolds, but foundation of calculus on manifolds. I mean, you need a tangent space to do calculus on manifolds and stuff. So, first of all, let's just do the element, trivial manifold, which would just be Rn and stuff. And to do it on a manifold, we first of all need to describe one on Rn, right? What is a tangent space on Rn, right? Well, notice, first of all, well, yeah, so it's basically, alright, here's a vector and here's a point. The problem, though, is that the point is not at the origin, right? So usually when we say a vector, right, it's usually in terms of the origin, right? So we have like v1, v2, these are the two components of the vector, right? And this is usually with respect to the origin, so this would be v in this case, but we want it at p, right? So what this does, right, and really it's like it's a lot like a transformation of Rn, right? But this is much more important on manifolds. But in Rn, it basically moves the origin right here to p, right? Yeah, I guess that works. To a point on Rn, right? So it basically, what it does, really, is it takes every single possible vector emanating from P, right? It's the set of all possible vectors emanating from P, which would just make the vector space Rn, right? Or, yeah, this is R2 in this case, but yeah, it makes basically Rn, but at a different point, right? Because that's what R2 is. It's at 0 though, and these two vectors span all the way from 0. So every single possible vector is a set of all vectors emanating from P instead of 0. Now I'm going to give you a preview why this is helpful. So, well, actually, I hope you know, because if we have a geometric object, right, like this, I don't know why this is so standard at this point. I don't know if you've seen this multiple times, but I have seen this multiple times. So at a point right here, P, right? First of all, geometric objects cannot be vector spaces, right? They're curved, and they do not satisfy the vector space property, which they're not closed under addition, and they're not closed under, well, yeah, scalar multiplication and addition. You know, this thing, C alpha plus beta, right? Intuitively, it's curved. So, yeah, it's curved, so it's not a vector space, and it's not linear, because linear means straight. So that's the, I don't know, gay way to say it, but yeah. So at P, right, notice, okay, so this also gets into a derivation, right? It's a lot like a derivation, and I'm going to explain that. But yeah, so notice how you, first of all, can't build any vector space on manifolds and stuff, and you're always going to look at it locally, right? Okay, so this is why we're using this. But first of all, we're going to use this simple case, tangent space at Rn, right? All vectors emanating from P, right? That's all it is. I tried to explain this to somebody, but it did not go well. I really hope you get that in your brain. Yeah. Yeah. So we can really describe that as like P1 plus V1, P2 plus V2 and stuff. However, even with this and stuff, it still implies, like, it would still be like more like P plus V, right? It would look at P as a vector, and it would just take the total thing, right? So it's really hard to do this and stuff. So we need, like, something different. We need to differentiate it at some point and stuff, right? We'd always say, oh, the basis is at P and stuff, but, you know. Anyways, so because of that, each vector in Rn, right? This is each vector in Rn. We're going to express this, first of all, as the normal basis Vi, Ei. This also gets into why we use this, the up thing, for components, why we do I and Ei and stuff. Well, first of all, you would say that's tedious stuff, but I will get into why. So first of all, but as a glimpse, these basically cancel out. That's the idea over it. These cancel out, and then this creates this. Because this is a scalar, and this is a vector, which are two different things. This is a basis vector, and this is a scalar. Okay? So yeah, that's what we can write V as, and what we're going to write V as, right, in terms of its basis. That's going to be in terms of its basis, right? So notice how I was talking about manifold earlier, and, you know, how it emanates from P, right? Doesn't that a lot look like a derivation? Remember in calculus 3? I also expected you to do calculus 3. So I hope you did calculus 3. If you did not do calculus 3, get the fuck out of here and learn some calculus 3, because that is very much